Hello students, and welcome to section 4-6, Isosceles and equilateral triangles. Properties of isosceles triangles. An isosceles triangle has two congruent sides called the legs. The angle formed by the legs is called the vertex angle. The other two angles are called base angles. You can prove a theorem and its converse about isosceles triangles. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. This is called the isosceles triangle theorem. And it is also true that in this particular picture, if we were to designate that AB is congruent to CB, and we mark the picture as such, then we can argue that the angles opposite those sides, angle A and angle C, are also congruent. But again, it's the hypothesis of sides being congruent and then the conclusion of angles. However, we can also take the converse of this statement and it also be true. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. Again, the converse of the isosceles triangle theorem, which if you can again see here, you've got angles congruent first. So let's say we start with angle A congruent to angle C. If that's the case, then side AB must be congruent to side CB. So if sides, then angles, or if angles, then sides. You need to be familiar with both the isosceles triangle theorem and its converse. They're both true. Example 1. Find x given BC is congruent to BA. Okay, so right away, if you take a look at the picture, knowing that the sides are congruent, so BC is congruent to BA, and let's also kind of help mark things as according to what we saw at the beginning as such. So we know that this is a leg, as well as this. They're both legs. Okay, so as far as what we know for sure, thanks to the idea that the legs are congruent, right, we also then have to argue that the angles opposite are also congruent. So these two angles are congruent. And they say that right away. I just marked it. Please do so as well. But if you note here, as they noted, BC is equal to BA, not just the congruency statement that we see up above is true. We also know that it's true that the measure, so if you know the value of one, you know the value of the other. And the same, of course, holds true as we indicated up above. If sides congruent, then angles congruent. So angle A, the measure of it, is equal to the measure of angle C. That is the isosceles triangle theorem. We can set, therefore, 5x minus 10, that angle equal to the other angle, 4x plus 5. Simply subtract 4x, and then add 10. So what? 10 plus 5, of course, is 15. So that's the value of x. You can plug it back in to find the measure of each respective angle, but it will work if you do that. If you'd like to test it, please do so. Example 2, find x. So we see our picture. Now, we are not told word-wise, what is true. We see in the picture, however, angle S is congruent to angle T, which should be obviously the converse of the isosceles triangle theorem, which tells us that if the base angles are congruent, then the sides opposite of those angles are also congruent. In other words, side SR is congruent to side TR. And they say that here in the statement, starting with the measure of angle S equal to the measure of angle T. So SR is equal to TR, the actual measure of those two sides. Yes, they're also congruent, both the angles and the sides, again because of the converse of the isosceles triangle theorem. But now we can argue that they're equal to each other. SR is equal to TR. So simply 3x minus 13 equals 2x. We subtract 2x, we add 13, so you end up with, as you can see here, it's subtracting 2x over here gives us x, and therefore you get x equal to 13. If you plug in 13 for x here and here, which you can try that out if you'd like, it didn't ask you to, but if you did, you'd end up with this side equal to that side, the actual measure. All right, let's move on. We've got some exercises, plus we have a little proof to take a look at as well. Find the value of each variable. So this picture hopefully designates quite nicely such that you see an isosceles triangle, but because the sides are marked accordingly, you know that these angles are congruent. Okay, we have a 40-degree angle. Because we're trying to find x, we can argue that this is also 2x, right? The base angles have to be congruent. So we can set ourselves up with the following algebraic equation. We can say that 2 times 2x plus 40 equals 180. Okay, so if we subtract, multiply as well, but subtract 40, we get this. And then if you divide by 4, 140 divided by 4, obviously we're looking at 35 for x. Please be careful, right? We're not asking for the angle values, but you could find the angle values by simply plugging it back in. If you did plug it in, 2 times 35, of course, is 70, and you have 2 of those, so 2 times 70, which is 140. 140 plus 40, of course, is 180. Okay, so let's move on. I think it would be nice to take a look at a couple more here. I think number 2 in particular is really nice, so let's take a look. And I'll probably have you go ahead and try a couple on your own as well, maybe later for notes. Because on number 2 we see the base angles are congruent, we also therefore can argue that the sides are congruent as such. So again, if base angles are congruent, then the legs or sides opposite those angles are also congruent. So we can set 2x plus 6 equal to 3x minus 6. Okay, I'm going to go ahead and subtract 2x. At the same time, I'll go ahead and add 6. So if we do that, we'll end up with 12 equals x. So for number 2, again, all you're solving for is x. If you did extend this a step or two farther, in other words, plugging in x, you have 2 times 2 plus 6, which of course is 10. And then times 12, pardon, 2 times 12 plus 6, which of course is 24 plus 6, so 30, pardon. So 3 times 12, all right, minus 6 should end up being, well, not surprisingly, the exact same result, right? 3 times 12, of course, being 36, minus 6 being, of course, 30. So each side is 30. Let's try another one. I do think it'd be wise for us to take a look at 5 and or 6. I think number 5 in particular, because it's a right triangle, and because also it's an isosceles right triangle, like number 1, not too difficult though, I would say, because the sides are congruent, we know these two angles are congruent. So that angle, of course, must also be 5x. So the approach is the same. However, on this problem, I think we'll take a little bit of a different route where, because we already know that the topmost angle, that vertex angle in other words, right, that vertex angle is 90, you know that the sum of the other two angles must equal 90 degrees. So you don't actually have to set it equal to 180. You could theoretically just do 2 times 5x equals 90. And then individually, you could even go as far as to set 5x equal to what? 45. And then divide, of course, and you end up with 45 divided by 5 to be 9. You are solving for x, so we'll leave it at that. Please pay attention to this type of problem, however, because as it turns out, this is not only an isosceles triangle, it's also something called a 45, 45, 90. A 45, 45, 90 right triangle will always have those dimensions, or those values, pardon, of the angles given the dimensions of which have two legs congruent. It has to be true. Always where an isosceles triangle has a right angle, the other two must each be 45 degrees. So again, this is a 45, 45, 90. If you wanted to just divide 45 by 5 without doing 2 times 5x equals 90, that would have been just fine as well, because again, each angle in a 45, 45, 90 isosceles right triangle has those measures. Okay, I think number 6 is a good finishing touch here for these little section of problems. We've got an isosceles triangle. We also therefore can argue that these two are congruent. Therefore, this is also x. Remember that the angles are going to add up to 180 degrees, so we could do 2x plus 3x equals 180. Okay, if we finish this, we've got 5x equals 180. And of course, if we divide both sides by 5, we should end up with x equals 36. Okay, again, if you plugged in 36, you should find that all angles, in fact, will add up to 180. 2 times 36 plus 3 times 36 does in fact equal 180. All right, this next problem is a proof. It's a 2-column proof. We're going to go ahead and look at, given the angle 1 congruent to angle 2 in the picture, mark it please, prove that side AB is congruent to side CB. So I do want to make the comment again, as I've done many times, that even though you're given a certain piece of information, you can still mark and should still mark your picture as much as you possibly can if you know something is true. Particularly, you know that angle 2 is congruent to angle 3. And again, if you're wondering why, think about vertical angles. Vertical angles are congruent. So you can already see that angle 1 is congruent to angle 3 by virtue of the transitive property. So start thinking a little bit in advance how this is going to unfold. And because the base angles are congruent, it shouldn't come as a big surprise. If the base angles are congruent, therefore the sides must be congruent. That is the converse of the isosceles triangle theorem. Okay, so let's take a look. Step 1, given. Angle 1 is congruent to angle 2. Step 2, angle 2 is congruent to angle 3, again by virtue of vertical angles being congruent. And then next, step 3, angle 1 is congruent to angle 3 by the transitive property of congruence. We already knew these in advance. And then last but not least, we know for a fact that AB must be congruent to CB by the converse of the isosceles triangle theorem. Pretty nice little proof, not too labor intensive, but it does still get to the point, of course, of what we're trying to get through for today. Let's move on to the next page. I'd like to get through at least the example on this next page. It says properties of equilateral triangles. An equilateral triangle has 3 congruent sides. The isosceles triangle theorem leads to 2 corollaries about equilateral triangles. First, a triangle is equilateral if and only if it is equiangular. So remember, it can go in both directions. You can say if a triangle is equilateral, then it's equiangular, or you can say if a triangle is equiangular, then it's equilateral. So this is an if and only if. It goes in 2 directions, a biconditional. The other corollary, each angle of an equilateral triangle measures 60 degrees. And that makes sense if you think about if it's equiangular, and if all angles add up to 180, what's 180 divided by 3? Of course, that's 60. Okay, so equiangular implies obviously 60 degrees for each angle. And if it's equilateral, it's also equiangular. So equilateral implies that each angle is 60 degrees. All right, example. Prove that if a line is parallel to one side of an equilateral triangle, then it forms another equilateral triangle. Okay. So the first step of this proof, and you can see the picture, you've got 2 sides that are parallel. Okay, there's some really neat things you can identify with and should identify with just by virtue of looking at the picture. But because what we're provided in the picture, there's some things we should kind of go through even after we identify in the picture what we see, but also in the sense of what the given really is. So first, it is an equilateral triangle, ABC. I'm not going to attempt to mark the way I usually do. So that side is congruent to that side, which is congruent to that side. Okay, PQ is also parallel to BC. We see that marked. That's given. Angle A is equal to angle B, which is equal to angle C. So these 3 angles are all 60 degrees. Okay, we can mark them actually accordingly. They're all congruent, and yes, they're all 60. I won't go as far as to fill in 60, but we know that's true. The reason each angle of an equilateral triangle measures 60. Angle 1 is congruent to angle B, and angle 2 is congruent to angle C. If parallel lines, then corresponding angles are congruent. In other words, 1 and B, 2 and C. Those are corresponding angles. Those are congruent. Those are congruent. Angle 1 is 60 and angle 2 are 60. By substitution, you know those have to be, of course, 60 because those are 60. And then last but not least, triangle APQ is equilateral, the smaller of the 2 triangles, APQ. because you have another an angle of 60, another angle of 60, and then yet again a third angle of 60. So not only is triangle ABC equiangular and therefore equilateral, triangle APQ is equiangular and also equilateral.